Hello there, and welcome to the Sleepless Scientist. Tonight we're exploring something so familiar, we often forget its wonder: water. It's in the oceans that cover most of our planet, in the clouds drifting overhead, in every cell of your body. Water has traveled from the stars to shape our world, carving mountains, nurturing life, connecting everything in an endless cycle. It's both simple and mysterious, common yet extraordinary. As you settle in, let the story of water wash over you gently, like rain on leaves or waves on sand. Let it remind you that you're part of something ancient and ever-flowing, something that connects you to the beginning of the earth itself. And just before we begin, if these calm, curious explorations help you unwind or give you a quiet way to end your day, consider liking and subscribing to the channel. It helps others find their way here too, one sleepy soul at a time. The story of water begins. Water's story is older than Earth itself. Long before our planet formed, water existed in the cold reaches of space, frozen into comets and asteroids drifting through the void. Hydrogen, the universe's most abundant element, combined with oxygen, forged in dying stars to create HO molecules. These simple arrangements of three atoms would become the foundation of life as we know it. When the early solar system was still a chaotic disk of dust and gas, water was already there, hidden in ice and rock. Some of it would eventually find its way to a young, molten world, orbiting at just the right distance from the sun, not too close to boil away, not too far to freeze permanently. That world was Earth. The story of water is a story of cosmic coincidence and chemical necessity, of violence and patience. It's a story that began in the hearts of ancient stars and continues in every raindrop, every river, every ocean wave. Water didn't just arrive on Earth. It helped create the conditions for everything we know, shaping the planet and making it habitable. The story of water is in many ways the story of life itself, the substance that shapes the world. Water is unlike any other substance. It exists in three states: solid, liquid, and gas. Within the narrow temperature range we experience on Earth's surface. This versatility makes it uniquely powerful. As a liquid, it flows, erodes, transports, and dissolves more substances than any other solvent. As ice, it carves valleys and breaks rocks. As vapor, it stores and moves energy across the atmosphere, driving weather and climate. Water shapes landscapes. Rivers cut through continents over millions of years, carrying sediment from mountains to seas. Glaciers grind down stone, sculpting valleys and peaks. Rain weathers rock, slowly releasing minerals that feed soil and ecosystems. Even the oceans shape coastlines, their waves constantly reshaping beaches and cliffs. But water doesn't just shape the physical world, it shapes life. Organisms evolved in water and carry it within them. Water determines where life can exist, from desert oases to deep ocean vents. It moderates Earth's temperature, preventing extremes that would make life impossible. The substance that shapes the world is simultaneously the substance that sustains it. Water is sculptor and source, destroyer and creator, flowing through time in an endless transformation that has shaped everything we see. The ancient origins of water on Earth. How did Earth get its water? Scientists believe it came from multiple sources over millions of years. When Earth first formed about 4.5 billion years ago, it was a molten ball bombarded by asteroids and comets. Some of those impactors carried water ice, delivering it during the violent early period called the Late Heavy Bombardment. But not all water came from space. Some was likely trapped inside the minerals and rocks that formed Earth itself, released over time through volcanic activity. As the young planet cooled, water vapor in the atmosphere condensed and fell as rain, torrential rains that may have lasted for millions of years, gradually filling the ocean basins. The ancient origins of water on Earth are still debated. Did most come from asteroids? From comets? From the planet's interior? Probably all three contributed. What's certain is that water arrived early and stayed, held by Earth's gravity, and protected by its magnetic field from being stripped away by solar wind. Those ancient water molecules are still here, cycling through oceans, clouds, and living things. The water you drink today might once have fallen on primordial seas, been swallowed by dinosaurs, or frozen in ancient glaciers. It connects us to Earth's deep past. The journey of a drop through time. Imagine a single water molecule. It formed billions of years ago, perhaps in a comet's icy heart or deep within Earth's mantle. Eventually, it reached the surface, becoming part of the first oceans. Over geological time, it has cycled endlessly, evaporated by the sun, carried aloft as vapor, condensed into clouds, fallen as rain. That drop might have landed in ancient seas where the first life emerged. It might have been absorbed by a trilobite, cycled through prehistoric forests, or frozen in ice sheets that covered continents. It could have flowed down rivers that carved the Grand Canyon, or gathered in lakes now long vanished. Through all of Earth's history, mass extinctions, continental drift, the rise and fall of species, this molecule has journeyed. It's been rain and snow, river and sea, cloud and glacier. It's been inside countless organisms, part of their cells and blood and breath. Today, that drop might be in the ocean, waiting to evaporate again, or in a river rushing toward the sea, or falling as rain on your window. The journey of a drop through time is the journey of Earth itself, a story of transformation without end, connection without boundary. How water came from the stars. Water's ingredients were born in stars. Hydrogen formed in the Big Bang, the simplest and first element. Oxygen came later, created through nuclear fusion in the cores of massive stars. When those stars died, they scattered their elements into space through supernova explosions. In the cold regions between stars, hydrogen and oxygen found each other. On the surfaces of dust grains, shielded from harsh radiation, they bonded to form water molecules. These grains accumulated in clouds that eventually collapsed to form new star systems, including our own. Water was present in the disk of material that would become the solar system. It froze into ice on particles in the colder outer regions, beyond what's called the frost line. Some of this icy material became comets. Some was incorporated into asteroids, and some found its way to Earth. So when you drink a glass of water, you're consuming molecules with atoms forged in stellar furnaces, combined in the depths of space, delivered across billions of kilometers. Water came from the stars, carrying with it the raw materials of creation. It's stardust in liquid form, a cosmic gift that makes life possible. The cosmic chemistry of Hatho. Water is deceptively simple. Two hydrogen atoms bonded to one oxygen atom. Yet this simple arrangement creates remarkable properties. The molecule is bent, not straight, with the oxygen atom at the vertex. Oxygen hoards electrons, more than hydrogen does, making the oxygen side slightly negative and the hydrogen side slightly positive. This polarity makes water a powerful solvent. The positive end attracts negative ions. The negative end attracts positive ions, and substances dissolve. It's why salt disappears in water, why sugar sweetens tea, why water can carry nutrients through soil and bloodstreams. The bent shape and polarity also allow hydrogen bonding, weak attractions between molecules that give water its unusual characteristics. These bonds make water sticky, with high surface tension. You even it take more energy to heat than most substances. They make ice less dense than liquid water, allowing it to float. The cosmic chemistry of Hatho is a lesson in how simple components can create complex behavior. Three atoms, arranged just so, produce a substance essential for life. Change the angle or the elements, and you'd have something completely different. But with hydrogen and oxygen in this configuration, you have water, miraculous, ordinary, essential. The abundance of water in the universe. Water isn't rare in the universe. It's common. Astronomers have found it almost everywhere they look. Water ice exists on Mars, on moons, orbiting Jupiter and Saturn, in the rings of Saturn, in comets throughout the solar system. Beyond our neighborhood, water has been detected in interstellar clouds, in the atmospheres of planets orbiting distant stars, even in galaxies billions of light years away. Water forms wherever hydrogen and oxygen are present and temperatures allow, because hydrogen is the universe's most abundant element, and oxygen is common too. Created in stars, water emerges naturally throughout the cosmos. Some moons in our solar system likely have more water than all of Earth's oceans combined, locked beneath icy surfaces. Europa, Enceladus, and others may harbor subsurface oceans kept liquid by tidal heating. The abundance of water in the universe suggests that if life requires water, as all life on Earth does, then the conditions for life might be widespread. Water could be flowing, freezing, and evaporating on countless worlds, cycling through alien landscapes we'll never see. It connects Earth to the wider cosmos, a common thread woven through the fabric of existence. The formation of Earth's oceans. Once Earth cooled enough, water could remain liquid on its surface. Volcanic outgassing released water vapor, trapped in rocks, asteroids, and comets, delivered more water from space. The atmosphere grew thick with steam. As temperatures dropped below water's boiling point, condensation began. Clouds formed, towering and dark, and then it rained. This wasn't a brief shower. It may have rained for thousands or even millions of years, a perpetual downpour that gradually filled the low-lying basins of the young Earth's surface. The formation of Earth's oceans was a slow accumulation, water pooling, in depressions, collecting salt and minerals dissolved from rocks. At first, the oceans were likely very different from today, hotter, more acidic, filled with dissolved iron that gave them a greenish tint. Over time, chemical reactions and the emergence of life changed the ocean's composition. Photosynthetic organisms produced oxygen, which reacted with iron, causing it to precipitate and settle, forming massive iron deposits. The oceans we know today, blue, salty, teeming with life, are the product of billions of years of evolution, both geological and biological. They're ancient, yet ever-changing, a planetary feature that has existed almost as long as Earth itself. The first rain that fell on the planet. Imagine the first rain, the sky, thick with clouds, finally cool enough for water vapor to condense, droplets forming, growing heavy, beginning to fall. The first raindrops in Earth's history struck a barren surface of volcanic rock, still hot from the planet's violent formation. They hissed and steamed on contact, evaporating instantly, but more kept falling. Gradually, the surface cooled, puddles formed, streams began to flow, carving the first channels in the rock. Water pooled in low areas, creating the first lakes and proto-oceans. The first rain was likely acidic, filled with dissolved gases from the volcanic atmosphere, carbon dioxide, sulfur dioxide, creating weak acids that weathered rock and released minerals. This rain fell on a world without life, without soil, without vegetation to slow its flow. It was purely a physical process, water meeting stone, beginning the slow work of erosion and chemical transformation that would eventually create conditions suitable for life. The first rain that fell on the planet was the beginning of a process that continues today. Billions of years later, rain still falls, still shapes the land, still sustains life. That first rain set in motion a cycle that has never stopped. The endless cycle of water. Water moves in a cycle with no beginning or end. It evaporates from oceans, lakes, rivers, and soil, rising as invisible vapor into the atmosphere. It's released by plants through transpiration, moisture breathed out through leaves. In the air, vapor cools and condenses around dust particles, forming clouds. When droplets grow large enough, they fall as precipitation, rain, snow, sleet, or hail. On the ground, water flows into streams and rivers, making its way back to the sea. Some soaks into soil, recharging underground aquifers. Some is absorbed by plants and animals, becoming part of their bodies temporarily before being released again. The endless cycle of water connects earth, sea, and sky. It moves energy around the planet, distributing heat from the tropics to the poles. It shapes climate and weather. It sustains ecosystems and civilizations. The cycle operates on multiple timescales. A raindrop might complete the cycle in days, while water locked in a glacier might take thousands of years to return to the sea. But it always moves, always transforms, never truly created or destroyed, just changing form and location. The water cycle is one of Earth's fundamental processes, a planetary heartbeat that has pulsed for billions of years. Evaporation and return. Evaporation is water's escape. Energy from the sun strikes the ocean's surface. Rivers, lakes, even puddles, water molecules, absorb that energy and break free from the liquid's surface tension, rising as vapor into the air. This happens constantly, invisibly, on every body of water exposed to air. The warmer the water and air, the faster evaporation occurs. Tropical seas evaporate faster than polar ones. Shallow water evaporates faster than deep. Evaporation is how water enters the atmosphere, beginning its journey through the sky. But what rises must eventually return. As vapor rises, it cools. Cool air can't hold as much moisture as warm air. Eventually, the vapor condenses, forming clouds. When clouds become saturated, precipitation falls, rain returns water to the surface. This evaporation and return is the engine of the water cycle, powered by the sun. It's a simple process with profound consequences. Without evaporation, there would be no rain, no rivers fed by distant oceans, no moisture carried inland. Deserts would expand. Life would cling to coastlines. Evaporation and return connects land and sea, distributing fresh water across continents, making vast inland regions habitable. It's a quiet miracle, happening constantly, water leaving the sea and coming back, endlessly circulating. Clouds forming in the sky. Clouds are water in transition, suspended between Earth and space. They form when rising air cools and water vapor condenses around tiny particles, dust, salt crystals, pollen. These particles, called condensation nuclei, provide surfaces where vapor can transform into liquid droplets. Billions of these droplets cluster together, creating the visible mass we call a cloud. Clouds come in endless varieties: high, wispy cirrus made of ice crystals, puffy cumulus that dot summer skies, low gray stratus that blanket the horizon, towering cumulonimbus that spawn thunderstorms. Each type forms under different conditions: temperature, humidity, atmospheric pressure, and wind patterns all play roles. Clouds are not static. They constantly evolve, droplets forming and evaporating, shapes shifting in the wind. They can last minutes or persist for hours, traveling hundreds of kilometers before dissipating. Watching clouds form in the sky is watching water in motion, the atmosphere's choreography made visible. Clouds also play crucial roles in climate, reflecting sunlight back to space and trapping heat near Earth's surface. They're beautiful, yes, but also functional, part of the planet's temperature regulation system. Clouds forming in the sky remind us that water doesn't just sit still. It moves, transforms, connects the heavens and the earth. The weight of falling rain. Rain seems gentle, each drop tiny and light, but collectively, rain is heavy. A single raindrop weighs about 50 milligrams. A moderate rainfall of 1 inch over 1 square mile deposits over 72 million gallons of water, roughly 300,000 tons. That weight falls from the sky, striking leaves, roofs, soil, water. The impact is soft per drop, but substantial in aggregate. Rain nourishes, but also erodes. It fills rivers that can flood. It saturates soil that can slide. The weight of falling rain has shaped Earth's surface for eons, wearing down mountains, grain by grain, carving valleys, carrying sediment from highlands to lowlands and eventually to the sea. In tropical regions, intense rainfall can deposit feet of water in hours, overwhelming rivers and reshaping landscapes dramatically. In arid regions, rare rains cause flash floods, torrents of water transforming dry washes into raging rivers, briefly before vanishing again. The weight of falling rain is the weight of renewal and destruction, the force that waters life and erodes stone. Each storm is a redistribution of mass, moving water from sky to ground, from one part of the planet to another. And after the rain falls, it begins its journey back into soil, into plants, into streams, and eventually back to the sky. Rivers that carve the earth. Rivers are water's sculptors. They begin as trickles, rainwater gathering, springs emerging from hillsides, snow melt flowing downward. Gravity pulls water toward the sea, and along the way, it carves. Rivers pick up sediment, sand, pebbles, even boulders during floods. This material acts like sandpaper, grinding against the riverbed and banks, slowly deepening and widening the channel. Over millions of years, rivers carved deep canyons through solid rock. The Colorado River created the Grand Canyon, cutting down through layers of stone to expose nearly 2 billion years of geological history. Rivers meander, curving back and forth across floodplains, constantly reshaping their courses. They deposit sediment where the current slows, building deltas at their mouths where they meet the sea. These deltas are some of Earth's most fertile lands, enriched by nutrients carried from far upstream. Rivers that carve the earth connect mountains to oceans, high to low, wet to dry. They're arteries of the planet, transporting water and nutrients, shaping landscapes, sustaining ecosystems. Every river tells a story, written in stone and soil, a record of water's patient, relentless work, and they continue their work today, carving infinitesimally slowly, shaping the world for eons to come. The gentle flow of streams. Not all water moves violently. Streams flow gently, winding through forests and meadows. Their currents soft and steady. They're small rivers, sometimes narrow enough to step across, shallow enough to wade. Yet streams are vital. They drain rainfall from hillsides, preventing erosion and flooding. They carry nutrients from uplands to lowlands, feeding ecosystems along their banks. Stream water is often clear, filtered through soil and gravel, cold from groundwater springs. Fish, insects, amphibians, and countless other organisms depend on streams. Trees and plants line their banks, roots stabilizing soil, leaves shading the water, keeping it cool. The gentle flow of streams creates a rhythm, a constant murmur that changes with seasons, rushing during spring snowmelt, slowing to a trickle in summer droughts. Streams connect landscapes, linking high elevations with rivers, and ultimately the sea. They're pathways for nutrients, organisms, and water itself. Walking beside a stream is calming. The sound, the movement, the play of light on water, these engage the senses gently. Streams remind us that not all forces need be dramatic to be powerful. Slow, steady flow over time accomplishes as much as any torrent. The gentle flow of streams is patience made liquid. The power of waterfalls. Waterfalls are places where rivers suddenly drop, plunging over cliffs into pools below. The power of falling water is immense. Gravity accelerates the flow, and the water strikes the base with tremendous force, carving plunge pools and eroding the rock face. Over time, waterfalls can move upstream, the constant pounding undercutting the cliff until sections collapse. Niagara Falls, for example, has retreated several kilometers over the past 12,000 years. Waterfalls create unique environments. The constant spray nourishes mosses and ferns clinging to rocks. The mist cools the air. The sound is overwhelming, a roar that drowns out everything else. Standing near a large waterfall, you feel the power viscerally. The ground vibrates. The air is thick with moisture. The sound fills your chest, Waterfalls also generate negative ions, which some believe have mood-lifting effects. Whether or not that's true, there's no denying the awe they inspire. They're beautiful and dangerous, places where water's power is undeniable. The power of waterfalls has been harnessed by humans for millennia, first with water mills grinding grain, now with hydroelectric dams generating electricity. Yet even harnessed, water's power commands respect. Waterfalls remind us that water, patient and gentle in streams, can be ferocious when gravity and volume combine. The hidden life of lakes. Lakes are landscapes unto themselves, bodies of water surrounded by land, ranging from small ponds to vast inland seas. They form in depressions left by glaciers, in volcanic craters, behind natural dams of rock or ice, or where tectonic forces create basins. Lakes are layered ecosystems. Near the surface, sunlight penetrates, allowing photosynthetic algae and plants to thrive. Fish swim at various depths. The bottom layer, called the benthos, is home to worms, insects, bacteria that recycle nutrients. Temperature stratifies lakes. Warm surface water doesn't mix with cold deep water in summer, creating distinct zones. In temperate regions, lakes turn over in spring and fall as temperatures equalize, mixing nutrients throughout. The hidden life of lakes is astonishing in its diversity. Microscopic zooplankton filter algae. Larger predators hunt smaller fish. Birds nest on shores and dive for food. Frogs and salamanders breed in shallow waters. Beneath the surface, invisible to casual observers, complex food webs operate. Lakes also serve human needs: drinking water, irrigation, recreation, transportation. Yet they're fragile. Pollution, invasive species, and climate change threaten lake ecosystems worldwide. The hidden life of lakes deserves protection. These still waters that reflect the sky and harbor worlds beneath. The calm of still waters. There's something profoundly peaceful about still water. A lake on a windless day becomes a mirror, perfectly reflecting sky, trees, mountains. The surface is glass smooth, disturbed only by occasional ripples from fish or insects. Still waters invite contemplation. They're quiet, patient, absorbing rather than demanding attention. Sitting beside still water, the mind often quiets. The reflection creates symmetry, doubling the world, blurring the boundary between earth and sky. Still waters are rare. Most water is in motion, rivers flowing, oceans churning, rain falling. Stillness requires particular conditions: shelter from wind, no strong currents, a basin that holds water without draining quickly, ponds, small lakes, wetlands, and calm weather. These are the places of stillness. But even still waters are alive. Beneath the surface, life continues. Microorganisms drift, fish navigate, plants grow. The stillness is only on the surface. The calm of still waters is a gift, a moment of pause in water's endless motion. It reminds us that rest is natural, that motion and stillness are both essential. Water doesn't always need to rush. Sometimes it simply holds, reflects, waits. And in that waiting, there's beauty and peace. The vastness of the ocean. The ocean is Earth's defining feature. It covers 71% of the planet's surface, holding 97% of Earth's water. From space, Earth appears blue, a water world with scattered land. The ocean is a single, interconnected body, despite our names for different sections: Pacific, Atlantic, Indian, Southern, Arctic. All are linked, water flowing between them in global currents. The ocean is vast beyond easy comprehension. The Pacific alone is larger than all land on Earth combined. Its deepest point, the Mariana Trench, plunges nearly 11 kilometers below the surface, deeper than Mount Everest is tall. The ocean's average depth is about 3.7 kilometers. Most of it is unexplored, a dark, cold realm we've only glimpsed. The vastness of the ocean shapes climate, absorbs carbon dioxide, produces much of our oxygen through phytoplankton photosynthesis. It regulates temperature, moderating extremes. Coastal regions have milder climates than inland areas because the ocean stores and releases heat slowly. The ocean also provides food, transportation routes, and recreation for billions of people. Yet despite its size, the ocean is vulnerable. Pollution, overfishing, acidification, warming, all threaten ocean health. The vastness of the ocean can make us complacent, assuming it's too big to harm. But every part is connected, and damage spreads. The surface that reflects the sky. The ocean's surface is a boundary between worlds, the interface where sea meets sky. From above, it's a vast expanse of blue or gray, its color determined by sky conditions, depth, and what's suspended in the water. On calm days, it reflects the sky like a mirror, clouds duplicating themselves on the water. From below, looking up, the surface appears silvery, reflecting light back down due to the difference in refractive index between water and air. The surface is also a barrier. Most marine life never crosses it. Fish see a world bounded above by that silvery ceiling. Seabirds see it from above, diving through briefly to snatch prey before returning to air. The surface is dynamic, constantly moving. Wind creates waves, ranging from tiny ripples to towering swells. Waves carry energy across oceans, generated by storms thousands of kilometers away. Breaking waves release energy, accumulated over vast distances, crashing on shores with force that shapes coastlines. The surface that reflects the sky is also where gas exchange occurs. Oxygen dissolves into seawater. Carbon dioxide is absorbed. This exchange is vital for marine life and climate regulation. The surface is thin, a film between vast realms, yet crucial, active, beautiful in its constant motion. The layers of the sea. The ocean has layers, each with distinct characteristics. The sunlit zone, or epipelagic, extends to about 200 meters. Light penetrates here, allowing photosynthesis. Most marine life inhabits this layer. Fish, dolphins, sharks, sea turtles, plankton. Below lies the twilight zone, the mesopelagic, from 200 to 1,000 meters. Faint light filters down, but not enough for photosynthesis. Creatures here often have large eyes or bioluminescence to navigate the dim waters. Deeper still is the midnight zone, the bathypelagic, from 1,000 to 4,000 meters. Total darkness prevails. Hull pressure is immense. Temperatures hover near freezing. Yet life persists. Bizarre fish with sharp teeth, squid, jellyfish, adapted to the cold and dark. The abyssal zone, 4,000 to 6,000 meters, covers vast areas of the deep ocean floor. Life is sparse but includes specialized organisms near hydrothermal vents. Finally, the hadal zone encompasses the deepest trenches, below 6,000 meters. Few creatures survive here, but those that do are uniquely adapted to crushing pressure. The layers of the sea create vertical ecosystems, each with its own communities, challenges, and adaptations. Exploring these layers reveals that the ocean isn't uniform. It's a complex, three-dimensional environment, as varied as any terrestrial landscape. The warm currents that shape the climate. Ocean currents are rivers within the sea, vast flows of water circling ocean basins and connecting them globally. Some currents are warm, carrying heat from the tropics toward the poles. The Gulf Stream, for example, transports warm water from the Gulf of Mexico along the eastern United States coast and across the Atlantic toward Europe. This current moderates Europe's climate, keeping it warmer than other regions at similar latitudes. Without the Gulf Stream, places like Britain and Norway would be far colder. Warm currents, like the Kuroshio in the Pacific and the Agulhas along Africa's east coast, play similar roles, distributing heat and influencing regional climates. These currents are driven by wind, Earth's rotation, and differences in water density. They're part of a global conveyor belt, a system of currents that circulates water throughout the world's oceans over centuries. The warm currents that shape the climate are essential to Earth's habitability. They prevent the tropics from overheating and the poles from becoming even colder. They influence rainfall patterns, storm tracks, and marine ecosystems. Disrupting these currents, through climate change, for instance, could have profound consequences. The ocean's currents are like the planet's circulatory system, moving heat, nutrients, and life across the globe. The deep, cold waters below. Beneath the warm surface layer, the ocean is cold. Below about 1,000 meters, temperatures drop to just a few degrees Celsius and stay there, even in the tropics. The deep ocean is a vast, cold reservoir, accounting for most of the ocean's volume. This cold water forms at the poles, where surface water cools, becomes denser, and sinks. It then spreads along the ocean floor toward the equator, moving slowly, taking centuries to circulate. These deep, cold waters are part of the thermohaline circulation, driven by temperature and salinity differences. They play a crucial role in storing heat and carbon dioxide, buffering the climate system. The deep ocean absorbs much of the excess heat from global warming, slowing surface temperature rise, but also storing that heat for eventual release. Deep cold waters are nutrient-rich. When they rise to the surface in upwelling zones, they bring nutrients that fuel phytoplankton blooms, supporting rich fisheries. Yet the deep ocean remains largely unexplored. It's dark, high pressure, and difficult to access. Only a handful of humans have visited its deepest points. The deep, cold waters below are a frontier, a reminder that Earth still holds vast, mysterious realms we've barely begun to understand. The dance of waves and wind. Waves are the ocean's visible rhythm, rising and falling in endless motion. They're created by wind blowing across the water's surface, transferring energy. The size of waves depends on wind speed, duration, and fetch, the distance over which the wind blows. A gentle breeze creates ripples. A sustained gale creates swells that can travel thousands of kilometers. Waves don't move water forward in the open ocean. They move energy. Individual water molecules mostly rise and fall in circular paths. It's only near shore, where the bottom shallows, that waves break, water tumbling forward onto the beach. The dance of waves and wind is mesmerizing. Watching waves roll in, one after another, is hypnotic. The sound, crashing breakers or gentle lapping, has a rhythm that soothes. Waves shape coastlines, eroding cliffs, depositing sand, creating beaches. They're also powerful. Storm waves can reach heights of 30 meters or more, capable of moving boulders and destroying structures. Surfers ride waves for sport, harnessing their energy briefly. Engineers capture wave energy for electricity, but mostly, waves just are constant, beautiful, the ocean's breath made visible. The dance of waves and wind connects atmosphere and sea, a partnership playing out across every ocean, every day. The rhythm of the tides. Tides are the ocean's slow heartbeat, rising and falling twice daily in most places. They're caused by the gravitational pull of the moon, and, to a lesser extent, the sun. The moon's gravity pulls on Earth's water, creating a bulge on the side facing the moon, and another on the opposite side. As Earth rotates beneath these bulges, any given location experiences high tide twice a day. When the sun and moon align, at new and full moons, their gravitational forces combine, creating higher high tides and lower low tides, called spring tides. When they're perpendicular, at the quarter moons, their forces partially cancel, creating weaker neap tides. The rhythm of the tides is predictable, calculable centuries in advance. Yet local geography complicates things. Bays and channels can amplify tides. The Bay of Fundy in Canada has the world's highest tides, over 15 meters in range. Other places experience microtides, barely noticeable. Tides affect marine life profoundly. Intertidal zones are alternately submerged and exposed, requiring specialized adaptations. Tides also influence human activities. Fishing, navigation, coastal development. The rhythm of the tides connects us to celestial mechanics, a reminder that Earth isn't isolated. The moon tugs on our oceans, linking sky and sea in an ancient, ongoing dance. The pull of the moon and sun. The moon and sun shape Earth's waters from afar. Though the sun is vastly more massive, the moon is much closer, so its gravitational effect on tides is stronger, about twice the sun's. This tidal force isn't uniform across Earth. The side facing the moon feels a stronger pull than Earth's center, and the center feels a stronger pull than the far side. This differential force stretches Earth slightly, creating the two tidal bulges. Tidal forces affect not just oceans, but Earth's crust, though the effect is much smaller. The solid Earth rises and falls about 30 centimeters daily, imperceptible without sensitive instruments. Tidal forces also have long-term effects. Friction between tidal bulges and Earth's rotation slows Earth's spin, lengthening days by about 2 milliseconds per century. The moon, in turn, slowly drifts away from Earth, about 4 centimeters per year. Billions of years ago, the moon was closer, days were shorter, and tides were larger. The pull of the moon and sun is a cosmic connection, celestial bodies influencing Earth's waters across the void of space. It's a reminder that we're part of a solar system, interconnected through gravity, our planet's rhythms shaped by its neighbors. The breath of the ocean. The ocean breathes. It absorbs carbon dioxide from the atmosphere and releases oxygen, though less than often claimed. Phytoplankton produce much oxygen, but ocean bacteria consume most of it. The net contribution is significant historically, but modest currently. Still, the ocean absorbs about a quarter of human-emitted CO2 annually, slowing atmospheric buildup and climate change, though at a cost. Absorbed CO forms carbonic acid, lowering ocean pH, making seawater more acidic. This acidification threatens shell-forming organisms, like corals, mollusks, and some plankton, with cascading effects through food webs. The ocean also absorbs and releases heat, moderating Earth's temperature. Warm water holds less dissolved gas than cold, so as oceans warm, they release some absorbed CO, creating a feedback loop. The breath of the ocean is a gas exchange, continuous and vital. Phytoplankton near the surface photosynthesize, producing oxygen and consuming CO. When they die, some sink, carrying carbon to the deep sea, where it's stored for centuries. This biological pump helps regulate atmospheric CO. The breath of the ocean is quiet, invisible, yet essential. It's a planetary process, connecting atmosphere, ocean, and life, part of Earth's complex climate system. Understanding this breath is crucial as we alter the atmosphere and warm the planet. The water that moves life across the world. Water is life's courier. Rivers carry nutrients from mountains to seas. Ocean currents transport plankton, fish larvae, and nutrients across thousands of kilometers. Water inside organisms moves substances between cells, from roots to leaves, from lungs to tissues. Without water's movement, life would be local, isolated. Instead, water connects ecosystems globally. Salmon hatch in freshwater streams, migrate to the ocean, then return years later to spawn where they were born. They bring ocean nutrients back to rivers, feeding bears, eagles, and forests. Whales migrate thousands of kilometers, following food sources, and their feces fertilize surface waters, supporting plankton that feed other species. Water that moves life across the world creates connections. A drop of rain in Colorado might end up in the Gulf of Mexico, carrying dissolved minerals that nourish plankton eaten by shrimp caught by fishermen. Water's movement redistributes resources, making life possible in places far from where those resources originate. Desert oases exist because underground water travels from distant mountains. Coastal wetlands thrive on sediments carried by rivers from hundreds of kilometers inland. Water that moves life across the world is both medium and message, carrier and catalyst. It shapes migration patterns, nutrient flows, and the distribution of species. Without water's constant circulation, Earth would be a collection of isolated ecosystems rather than an interconnected web of life. Water is the thread that weaves everything together, the source of every living thing. Life began in water. The first cells emerged in ancient oceans, perhaps near hydrothermal vents, where chemistry was rich and energy abundant. For billions of years, life was exclusively aquatic. When organisms finally colonized land, they brought water with them, cells filled with salty fluid, resembling the primordial sea. Every living thing on Earth depends on water. It's the medium where biochemical reactions occur. Enzymes function in aqueous solutions. DNA's double helix is stabilized by water molecules. Proteins fold into functional shapes, influenced by their interactions with water. Water is so fundamental to life that astrobiologists searching for life elsewhere look first for water. No known organism can survive without it, though some can endure desiccation temporarily by entering dormancy. The source of every living thing is water, not metaphorically, but literally. Life's chemistry requires water's unique properties, its ability to dissolve substances, maintain stable temperatures, participate in reactions. Remove water, and life as we know it becomes impossible. Every organism, from bacteria to blue whales, from desert cacti to rainforest trees, is fundamentally an aqueous system. We are all water-based life, carrying the ocean within us, descendants of creatures that first stirred in ancient seas. The water within our bodies. Your body is mostly water. An adult human is roughly 60% water by weight, though the percentage varies with age, sex, and body composition. Infants are about 75% water. The elderly may be 50%. Fat tissue contains less water than muscle, so leaner individuals have higher water percentages. This water isn't passive. It's the medium for life's chemistry. Blood is mostly water, carrying oxygen, nutrients, and waste. Cells are water-filled compartments where proteins, enzymes, and DNA operate. Intercellular fluid bathes cells, allowing communication and transport. Water regulates body temperature through sweating and respiration. It cushions joints and organs. It aids digestion and elimination. The water within our bodies must be constantly replenished. We lose water through urine, sweat, breathing, even tears. Dehydration quickly affects function. Concentration wanes, fatigue sets in. Eventually organs fail. Yet despite water's importance, the specific molecules are temporary residents. Water you drink is absorbed, used, and excreted within days. The water in your body today isn't the same water from last week. You're a flowing system, water passing through constantly, yet always maintaining that critical 60%. The water within our bodies connects us to the planet's hydrological cycle, temporary vessels for water's endless journey. The percentage that makes us alive, that 60%, isn't arbitrary. It's essential. Life's chemistry requires specific concentrations, specific conditions that only adequate water provides. Drop below critical hydration levels, and processes fail. Enzymes don't function properly. Blood thickens, straining the heart. Cells shrivel. The brain, which is about 75% water, is especially sensitive. Even mild dehydration impairs cognitive function, mood, and coordination. Lose 10% of body water, and you're in serious danger. Lose 15 to 20%, and death becomes likely. The percentage that makes us alive is maintained through constant regulation. Kidneys filter blood, retaining water when you're dehydrated, excreting excess when you're well hydrated. Thirst signals the need for intake. Hormones like vasopressin fine-tune water retention. This regulatory system evolved over millions of years, allowing terrestrial animals to survive away from constant water sources. Yet the margin is narrow. Humans can survive weeks without food, but only days without water, less in hot or dry conditions. Our dependence on that critical percentage is absolute. The water percentage in our bodies is life's minimum requirement, the foundation upon which all cellular processes rest. Maintaining it is a daily necessity, a reminder that we're never far from water's essential embrace. The importance of hydration in life. Hydration is maintenance of life itself. Every physiological system requires adequate water. Digestion begins with saliva, mostly water, and continues with water-rich gastric juices. Nutrients dissolved in water are absorbed through intestinal walls. Blood, 90% water, transports those nutrients to cells. Cellular metabolism produces waste that must be dissolved in water and eliminated via urine. Temperature regulation depends on water. Sweating cools the body through evaporation. Even breathing releases moisture. The importance of hydration extends beyond survival to performance and health. Athletes hydrate carefully because even mild water loss impairs endurance and strength. Students perform better on tests when adequately hydrated. Chronic mild dehydration may contribute to kidney stones, urinary tract infections, and other conditions. Different organisms have different hydration strategies. Desert animals conserve water through concentrated urine and minimal sweating. Aquatic organisms face the opposite challenge, maintaining the right internal salt concentration in a watery environment. Plants regulate water through stomata, balancing water loss against carbon dioxide intake. The importance of hydration in life cannot be overstated. Water is the medium of existence, the substance without which life's machinery grinds to a halt. Staying hydrated is honoring water's role in our biology. The chemistry of water molecules. Water's molecular structure explains its unusual properties. The oxygen atom has 8 protons and typically 8 neutrons. Each hydrogen has 1 proton. In an H2O molecule, oxygen shares electrons with 2 hydrogens, forming covalent bonds. But oxygen is more electronegative. It pulls electrons closer, making the oxygen region slightly negative and the hydrogen region slightly positive. This polarity makes water molecules attract each other. The positive hydrogen of one molecule is drawn to the negative oxygen of another, forming a hydrogen bond. These bonds are weak individually, but collectively powerful. Hydrogen bonds give water high surface tension. Insects can walk on it. They give water a high boiling point relative to similar molecules. Without them, water would boil at -80 degrees Celsius, and Earth would be lifeless. Hydrogen bonds also make water an excellent solvent. Polar substances dissolve easily as water molecules surround and separate ions or molecules. The chemistry of water molecules is elegantly simple, yet produces complex behavior. Those 3 atoms, bonded and polarized, create a substance unlike any other, essential for life, shaping landscapes, moderating climate. Understanding water's chemistry reveals why it's so special, why life chose it, why Earth's abundance of water makes it uniquely habitable among known worlds. The strength of hydrogen bonds. Hydrogen bonds are the secret to water's peculiar strength. Though much weaker than covalent bonds holding atoms together in molecules, hydrogen bonds collectively create remarkable cohesion. Water molecules cling to each other, forming networks. This cohesion creates surface tension, the tendency of water's surface to resist being broken. It's why water forms droplets rather than spreading infinitely thin. It's why small objects can rest on water's surface without sinking. Cohesion also creates capillary action, water's ability to flow through narrow spaces against gravity. Plants use capillary action and cohesion to draw water from roots to leaves, sometimes over 100 meters high. The water column doesn't break because hydrogen bonds hold molecules together. The strength of hydrogen bonds also gives water high heat capacity. It takes significant energy to break enough bonds to heat water, so water temperature changes slowly. This moderates Earth's climate. Oceans absorb summer heat and release it in winter, preventing extreme temperature swings. Ice formation involves hydrogen bonds arranging into a crystalline structure, more open than liquid water's random arrangement, which is why ice is less dense and floats. The strength of hydrogen bonds makes water uniquely suited to support life and shape Earth's environment. The strange properties of ice. Ice is water's solid form, yet it behaves strangely. Most substances are denser when solid than liquid. Molecules pack more tightly when they're not moving much. Not water. When water freezes, hydrogen bonds lock molecules into a hexagonal crystalline structure, with more space between molecules than in liquid water. Ice is about 9% less dense than water, which is why it floats. This strange property has profound consequences. Floating ice insulates the water below, preventing lakes and seas from freezing solid. If ice sank, it would accumulate on the bottom. Bodies of water would freeze from the bottom up, likely remaining frozen year-round in cold climates. Aquatic life would perish. Earth would be a very different, far less habitable planet. Ice also expands as it forms, exerting tremendous pressure. This breaks pipes, cracks rocks, and contributes to weathering. The strange properties of ice: lower density, crystalline structure, expansion on freezing, are all due to hydrogen bonding. That ice floats is an accident of chemistry, yet it's an accident that made complex life possible. The strange properties of ice remind us how finely tuned Earth's conditions are, how small differences in molecular behavior can have planetary consequences. Why ice floats on water. Ice floats because it's less dense than liquid water, a consequence of its crystalline structure. When water molecules slow down as temperature drops, hydrogen bonds begin locking them into position. At 0 degrees Celsius, they arrange into a hexagonal lattice, each molecule bonded to 4 neighbors in a rigid, open framework. This structure has empty space between molecules, making ice less dense than liquid water, where molecules are closer but randomly arranged. Density is mass divided by volume. Ice and water have essentially the same mass for a given number of molecules, but ice has greater volume due to its open structure, so its density is lower. Lower density means it floats. This seems simple, but is actually unusual. Almost all substances contract when they freeze. Their solid form sinks in their liquid form. Water's anomaly is due to hydrogen bonding's geometry. Why ice floats on water matters enormously. Ice on lakes and seas acts as insulation, maintaining liquid water beneath where life survives. Polar ice sheets reflect sunlight, helping regulate Earth's temperature. Ice floating enables the hydrological cycle to continue even in winter, with seasonal melting feeding rivers. If ice sank, Earth's climate and ecosystems would be unrecognizable. Ice floating is a fortunate quirk of physics that sustains life. The expansion when it freezes. Water expands about 9% when it freezes, a property rare among substances. As liquid water cools, it actually contracts until about 4 degrees Celsius, at which point it reaches maximum density. Below that, it begins expanding as hydrogen bonds start forming the open crystalline structure of ice. Upon freezing, expansion continues until the solid structure is complete. This expansion exerts considerable force. Water freezing in cracks can split rocks, a process called frost wedging that contributes significantly to erosion. Water in pipes can burst them, causing damage and flooding. Organisms must cope with this expansion too. Cells contain water, and ice formation can rupture cell membranes, which is why freezing kills most organisms. Some have evolved antifreeze proteins that prevent ice crystal formation or stabilize cell structures. Trees survive winter by moving water from cells into intercellular spaces where ice formation does less damage. The expansion when it freezes is a challenge. but also a force shaping the landscape. Mountains are gradually worn down, partly through repeated freeze-thaw cycles. Soil structure is influenced by ice expansion. The power of freezing water is underestimated until you've seen burst pipes or boulders split by ice. It's another reminder that water, seemingly gentle, possesses quiet, relentless force. The sound of breaking ice. Ice breaking creates distinct sounds, cracks, booms, tinkles. On frozen lakes, as temperatures shift, ice expands and contracts, creating stress. Sudden releases of this stress produce sounds ranging from sharp cracks to deep, resonant booms that can travel kilometers. These sounds can be startling, eerie, almost musical. Glaciers produce similar sounds. As they move, internal stresses build and release, creating groans and pops. Calving glaciers, where ice breaks off into water, produce thunderous roars and splashes. The sound of breaking ice is the sound of phase transition, solid yielding to liquid or pressure. Spring thaw creates a symphony, ice on rivers breaking apart, flows resuming, chunks colliding and grinding. The tinkle of ice cubes in a glass is miniature version, ear trapped in ice, escaping and tiny fractures forming. Listening to breaking ice is oddly compelling. It's a reminder of water's transformations, the forces acting on it, the temporary nature of ice's solidity. In a warming world, we hear more ice breaking, glaciers calving, ice sheets fracturing, permafrost thawing. The sound of breaking ice is becoming a soundtrack of climate change, beautiful and melancholy, marking transitions that will reshape our planet. The beauty of snow and frost. Snow is frozen water vapor that crystallizes directly from air into ice, forming intricate six-sided crystals. Each snowflake's shape depends on temperature and humidity during formation, creating nearly infinite variety. The saying that no two snowflakes are identical is essentially true. The number of possible arrangements is astronomical. Snow accumulates, blanketing landscapes in white, insulating the ground, reflecting sunlight. Frost forms when water vapor deposits directly onto surfaces as ice crystals, creating delicate, feathery patterns on windows, leaves, and grass. The beauty of snow and frost is ethereal, temporary artworks created by temperature and moisture. Snowflakes under magnification reveal stunning, geometric complexity. Frost patterns form dendrites and fern-like shapes. This beauty arises from physics, water molecules arranging according to hydrogen bonding geometry, variations in conditions creating variations in form. Snow and frost transform landscapes visually and functionally. Snow muffles sound, creating quiet. It provides water when it melts, critical for ecosystems and agriculture. It insulates, allowing life to persist beneath it through winter. The beauty of snow and frost is also a reminder of water's phases, its ability to shift forms, to create complexity from simplicity, to make the ordinary extraordinary. The magic of crystals in cold air. Ice crystals forming in cold air create phenomena that seem magical. Diamond dust is a cloud of tiny ice crystals suspended in air, common in polar regions. Sunlight refracting through these crystals creates halos, sundogs, and light pillars, optical effects that make the sky appear painted with light. Hoar frost forms when water vapor crystallizes on surfaces, creating delicate structures that catch sunlight and sparkle. Snow rollers form when wind rolls snow across the ground, creating cylindrical shapes like bales of hay. Ice fog consists of suspended ice crystals rather than water droplets, occurring when air is very cold and moist. The magic of crystals in cold air is physics, but it feels like enchantment. These phenomena occur when conditions align perfectly: right temperature, humidity, wind, sunlight. They're fleeting, often lasting only hours or minutes before melting or blowing away. Witnessing them feels like privilege. The magic of crystals in cold air reminds us that water's transformations create beauty everywhere, that the ordinary substance we drink and bathe in can become extraordinary given the right conditions. Ice crystals in cold air are water's art, sculptures formed and reformed, never the same twice, always beautiful. The formation of glaciers. Glaciers form where more snow accumulates in winter than melts in summer. Over years, centuries, millennia, snow compresses under its own weight, becoming firn, partially compacted snow, and eventually solid ice. The transition is gradual. Air is squeezed out, crystals fuse, density increases. Once thick enough, ice begins to flow under gravity, moving like extremely slow rivers. Glaciers carve landscapes, grinding rock into fine silt, creating U-shaped valleys, smoothing bedrock. They pluck boulders and carry them downslope, depositing them far from their origin. During ice ages, glaciers covered much of North America and Europe, profoundly shaping the terrain. Today's glaciers are mostly in polar regions and high mountains. They're shrinking as Earth warms, retreating faster than they advance. The formation of glaciers requires specific climate conditions: cold temperatures, sufficient snowfall, locations where snow can accumulate. Changes in these conditions change glacier extent. Glaciers are sensitive climate indicators. They respond to temperature shifts over decades. Their advance and retreat visible evidence of changing conditions. The formation of glaciers is a process still occurring in some places, but globally, we're watching the opposite. Glaciers melting, disappearing, leaving behind landscapes they shaped but will no longer occupy. The slow movement of ice across time. Glaciers move, though calling it movement seems generous. Typical rates are centimeters to meters per day, imperceptible, without time-lapse photography or measurement. Some surge periodically, moving tens of meters per day, briefly before returning to normal slow creep. Ice flows because under pressure, it deforms. The weight of accumulated snow and ice causes lower layers to become plastic, flowing like very thick honey. Glaciers flow downslope, toward warmer elevations, where they eventually melt. The slow movement of ice across time has shaped continents. During the Pleistocene ice ages, massive ice sheets advanced and retreated, bulldozing soil, scouring bedrock, carving the Great Lakes, creating the landscape of much of northern North America and Europe. Moraines, drumlins, kettles. These landforms result from glacial movement and deposition. Ice cores drilled from glaciers contain trapped air bubbles and dust from past millennia, providing climate records. Antarctica's ice sheet holds ice up to 800,000 years old, an archive of Earth's climate history. The slow movement of ice across time is both geological process and historical record, shaping land and preserving information. Glaciers are time machines, moving slowly but leaving lasting marks. The sculpting of mountains and valleys. Glaciers are sculptors. As they flow, they erode landscapes through two processes: abrasion and plucking. Abrasion is like sanding. Rock fragments embedded in the glacier's base scrape bedrock, polishing and scratching it. Plucking occurs when ice freezes onto bedrock, then tears away chunks as the glacier moves. Together, these processes carve distinctive features. Cirques are bowl-shaped hollows carved at glacier heads, often containing lakes after the ice melts. Arêtes are sharp ridges between adjacent glaciers. Horns are pyramidal peaks where multiple glaciers meet, like the Matterhorn. U-shaped valleys result from glaciers widening and deepening river valleys. Fjords are U-shaped valleys carved below sea level, later flooded when glaciers retreated. Hanging valleys are tributary valleys, left high above the main valley when a larger glacier carved deeper. The sculpting of mountains and valleys by glaciers creates dramatic, beautiful landscapes. Yosemite Valley is a glacially carved masterpiece. The Alps, the Rockies, the Himalayas all bear glacial signatures. Even where glaciers no longer exist, their work remains. Landscapes shaped by ice that flowed and retreated thousands of years ago. Glaciers sculpt slowly but powerfully, proving that patience and persistence can move mountains, or at least shape them. The melting that feeds the rivers. As glaciers melt, they feed rivers. Snow melt and ice melt from glaciers and snowpack is the primary water source for many rivers. Especially in summer, when precipitation is low, glaciers act as water reservoirs, storing precipitation that fell during winter or even centuries past, releasing it gradually. Rivers fed by glaciers tend to have high flows in late summer when melting is fastest, sustaining ecosystems and human water supplies during dry seasons. Many major rivers depend on glacial melt: the Ganges, Indus, and Brahmaputra in Asia, the Colorado in North America, rivers in the Andes supplying South American cities. As glaciers shrink due to warming, this water source is changing. Initially, melt increases, swelling rivers. Eventually, as glaciers diminish, summer flows will decrease, potentially causing water shortages for millions of people. The melting that feeds the rivers is a vital link between mountains and lowlands, cold and warmth, snow and sea. It's part of the hydrological cycle, moving water from storage to transport. But it's also a warning. Accelerated melting signals, climatic shifts. Rivers may run dry in summer, where they once flowed reliably. The melting that feeds the rivers is changing, and with it, the future of water availability for countless ecosystems and communities. The water hidden underground. Not all water is visible. Vast amounts lie underground in aquifers. Porous rock layers saturated with water. Groundwater fills spaces between sand grains, fractures in rock, and cavities dissolved in limestone. It's the source of springs and feeds rivers during dry periods. Groundwater accounts for about 30% of Earth's fresh water, far more than lakes and rivers combined. It accumulates slowly as precipitation percolates through soil and rock, sometimes taking decades or centuries to recharge. Once considered inexhaustible, many aquifers are being depleted faster than they refill. Agricultural irrigation, municipal water supplies, and industrial uses draw groundwater heavily. Some aquifers, called fossil water, accumulated during wetter ancient climates and aren't recharging significantly today. Pumping them is like mining a non-renewable resource. The water hidden underground is crucial for human civilization. Billions depend on it for drinking water. Ecosystems rely on groundwater-fed streams and wetlands, yet it's invisible, easy to overlook, until wells run dry. Groundwater moves slowly, invisibly, filtered and purified as it percolates through rock. It's a hidden reservoir supporting life above, a quiet, essential part of the hydrological cycle that deserves protection and careful management. The aquifers beneath our feet. Aquifers are underground layers of permeable rock or sediment holding water. Unconfined aquifers lie close to the surface, with water tables that rise and fall with rainfall. Confined aquifers are sandwiched between impermeable layers, often under pressure. Tap into a confined aquifer, and water may flow without pumping. An artesian well, the Ogallala Aquifer, beneath the Great Plains, is one of the world's largest, supplying 30% of U.S. irrigation water. It accumulated during the last ice age and is being depleted far faster than it recharges. Other major aquifers include the Guarani, beneath South America, the Great Artesian Basin in Australia, and aquifers beneath the Sahara, left from wetter periods. The aquifers beneath our feet are invisible infrastructure, nature's reservoirs. They filter water, removing many contaminants. They store vast quantities, buffering against drought, yet they're vulnerable to overuse, contamination from pollutants that seep downward, and land subsidence when water is removed and rock collapses. Managing aquifers requires understanding recharge rates, water quality, and sustainable pumping levels. The aquifers beneath our feet are gifts from the past, accumulated over millennia. Using them wisely is essential for future water security. The springs that rise from the earth. Springs are places where groundwater surfaces naturally, flowing out from rock or soil. They form where the water table intersects the land surface, or where impermeable rock forces water upward. Springs vary enormously. Tiny seeps, barely wetting the ground, or massive flows discharging millions of liters daily. Some are constant, others seasonal. Some are cold, others hot, heated by geothermal activity. Springs have supported human settlements for millennia, providing reliable water. They sustain ecosystems, feeding streams that might otherwise dry seasonally. Desert oases are often spring-fed, islands of life in arid landscapes. Hot springs host thermophilic bacteria that thrive in extreme heat. Mineral springs contain dissolved minerals from rocks, sometimes believed to have health benefits. The springs that rise from the earth are windows into the underground water system, revealing aquifer locations and conditions. Changes in spring flow can indicate drought, overuse of groundwater, or climatic shifts. Springs are also culturally significant, often considered sacred or healing. They're meeting points of earth and water, hidden and visible, underground and surface. Springs rising from the earth remind us that water is everywhere, even where we don't see it, flowing through the planet's depths, occasionally emerging into the light, the life that thrives in hidden waters. Underground water systems harbor life. Aquifers contain microbes, bacteria, and archaea that metabolize minerals and organic matter, filtering down from above. Some thrive in total darkness, in water that hasn't seen sunlight for thousands of years. Caves with underground rivers and lakes host unique species, blind fish, translucent crustaceans, adapted to eternal darkness. These troglobites have lost eyes and pigmentation, navigating by touch and chemical sensing. The life that thrives in hidden waters is adapted to scarcity, low nutrients, and extreme stability. Underground environments change slowly, with constant temperature and humidity. Species evolve specialized forms, often slow-growing and long-lived. Groundwater ecosystems are poorly studied and vulnerable. Contamination can poison them. Overpumping can dry habitats. Because they're unseen, they're often unprotected. Yet they're part of Earth's biodiversity, filling niches underground as diverse as those on the surface. The life that thrives in hidden waters reminds us that water sustains organisms in unexpected places, that ecosystems exist beyond our sight, beneath our feet. Protecting groundwater means protecting not just a resource, but living communities, microscopic and mysterious, adapted to life in darkness and water. The microcosms of ponds and pools. A pond is a world. Sunlight penetrates, allowing plants and algae to grow. Insects lay eggs in the water. Tadpoles transform into frogs. Fish, if the pond is large enough, patrol for food. Dragonfly larvae hunt smaller creatures. Snails graze algae. Bacteria decompose organic matter. Each pond is a microcosm, a complete ecosystem in miniature. Ponds are remarkably productive, supporting diverse life in small spaces. Temporary ponds fill with seasonal rains and dry up, yet they teem with life adapted to the cycle. Spadefoot toads that breed rapidly. Fairy shrimp, whose eggs survive desiccation for years. Even a roadside puddle lasting days can support mosquito larvae and algae. The microcosms of ponds and pools are laboratories for understanding ecology. Competition, predation, symbiosis, all occur in observable scales. They're also fragile. Pollution, draining, invasive species can destroy them quickly. Yet they're resilient too, recolonizing rapidly if conditions improve. Ponds connect landscapes, providing stepping stones for aquatic organisms. They're breeding sites, water sources, and refuges. The microcosms of ponds and pools are reminders that size isn't everything, that small waters can be as complex and important as large ones, that life flourishes wherever water gathers, however briefly. The living world's in a single drop. Under a microscope, a drop of pond water reveals an astonishing world. Paramecia swim, using countless cilia. Amoebas crawl, engulfing bacteria. Rotifers spin, filtering food with wheel-like ciliated crowns. Diatoms, single-celled algae with intricate glass shells, photosynthesize. Water fleas jerk through the water. Volvox colonies roll gracefully, hundreds of cells cooperating. The living worlds in a single drop contain dozens of species, hundreds or thousands of individuals. They represent multiple kingdoms of life: bacteria, protists, tiny animals. Each has its role: producers, consumers, decomposers, forming a miniature food web. These organisms exist almost everywhere. Water does. Soil water, puddles, lakes, oceans, all contain microscopic communities. They're the foundation of aquatic food webs, recycling nutrients, producing oxygen. Yet we rarely see them, going about our lives unaware of the teeming life in every water body. The living worlds in a single drop remind us of life's scale, its ubiquity, its diversity. They're beautiful under magnification, alien, yet earthly. They demonstrate that water isn't just habitat, it's a medium for stunning complexity, supporting life from the microscopic to the immense, all interconnected through the substance that makes life possible. The water in plants and trees. Plants are water-moving systems. Roots absorb water from soil. Xylem vessels transport it upward through stems and trunks to leaves, sometimes over 100 meters high in tall trees. This movement occurs through transpiration pull. Water evaporates from leaf surfaces, creating suction that pulls more water up from below. It's passive, requiring no energy input from the plant, just water's cohesion via hydrogen bonds. The water column doesn't break because molecules cling together. Plants use water for photosynthesis, combining it with carbon dioxide to produce sugars and oxygen. They use water to maintain cell pressure, staying rigid and upright. Wilt occurs when water pressure drops. The water in plants and trees is a significant part of the hydrological cycle. Trees transpire enormous amounts. A large oak can release over 150 liters per day. Forests create local humidity, contributing to cloud formation and rainfall. The Amazon rainforest generates much of its own rain through transpiration. Deforestation disrupts this cycle, reducing rainfall. The water in plants and trees connects soil, air, and climate. Plants are intermediaries, moving water from ground to atmosphere, shaping weather while sustaining themselves. They remind us that water's journey includes passage through living tissue where it sustains life before continuing its cycle. The cycle of transpiration. Transpiration is plant evaporation. Water leaving through tiny pores called stomata, mostly on leaf undersides. Stomata open to allow carbon dioxide in for photosynthesis, but also let water vapor out. Plants regulate stomatal opening to balance gas exchange against water loss. In dry conditions, they close stomata to conserve water, slowing growth. In moist conditions, they open wider, maximizing photosynthesis. The cycle of transpiration is crucial for moving water through plants and returning it to the atmosphere. About 10% of atmospheric moisture comes from transpiration, the rest from direct evaporation. Transpiration also cools leaves. Evaporation absorbs heat, preventing overheating in bright sunlight. The cycle connects plants to the broader water cycle. Water absorbed by roots is transported upward, used in photosynthesis, and released as vapor. That vapor rises, condenses, falls as rain, soaking soil, and is absorbed again by roots. The cycle of transpiration is elegant, using physics and biology to move water against gravity, sustain plant life, influence climate. It's another reminder that living and non-living processes intertwine, that organisms don't just exist within cycles, they drive them, participating actively in planetary processes that shape the environment for all life. The rainforest breath of moisture. Rainforests are water machines. Dense vegetation transpires enormous amounts of moisture. The Amazon rainforest releases roughly 20 billion tons of water vapor daily into the atmosphere. More than the Amazon River discharges into the ocean. This moisture rises, forms clouds, and falls as rain, much of it within the forest. The rainforest recycles its own water, creating a self-sustaining system. Cut the trees, and rainfall decreases, turning rainforest towards savanna or desert. The rainforest's breath of moisture doesn't stay local. Water vapor is carried by winds, influencing rainfall patterns hundreds or thousands of kilometers away. Rivers in the sky, atmospheric moisture streams, flow from the Amazon toward agricultural regions of Brazil and neighboring countries. This moisture supports farming, far from the rainforest itself. The rainforest's breath of moisture is part of global climate regulation. Tropical forests influence temperature, humidity, and rainfall worldwide. Deforestation disrupts these patterns, contributing to climate change beyond just carbon emissions. The rainforest's breath of moisture is life-giving, a planetary service provided by trees, water, and sunlight working together. Protecting rainforests means protecting water cycles, climate stability, and the countless species that depend on these living, breathing ecosystems. The clouds born from the forest. Above rainforests, clouds form constantly. The combination of heat, moisture from transpiration, and rising air creates perfect conditions. Warm, moist air rises, cools, and condenses into clouds that tower above the forest canopy. These clouds often produce afternoon rains, a daily rhythm in tropical regions. The clouds born from the forest are the forest's own creation. Water returned temporarily to the sky before falling back down. These clouds also reflect sunlight, cooling the surface and moderating temperature. They're part of the forest's microclimate: high humidity, moderate temperatures, frequent rain. The clouds born from the forest demonstrate feedback loops in Earth systems. Trees create conditions for rain, which sustains trees. Disrupting one disrupts the other. Satellite images show reduced cloud cover over deforested areas, less rain, higher temperatures. The clouds born from the forest are visible evidence of the link between vegetation and weather, between local ecosystems and regional climate. They're also beautiful, massive thunderheads building through the afternoon, releasing downpours, then clearing. The clouds born from the forest are nature's irrigation system, powered by sunlight and orchestrated by billions of leaves, breathing water into the sky. The role of water in weather. Water drives weather. Evaporation absorbs solar energy, storing it as latent heat in water vapor. When vapor condenses into clouds and rain, that energy is released, powering storms and atmospheric circulation. Hurricanes are heat engines, fueled by warm ocean water evaporating, condensing, releasing energy. This drives winds and rainfall, sometimes catastrophically. Thunderstorms form when moisture-laden air rises rapidly, condensing, releasing energy that strengthens updrafts. Water vapor is also a greenhouse gas, trapping heat and warming the atmosphere. It creates a feedback loop. Warmer air holds more moisture, which traps more heat. The role of water in weather extends to snow, hail, and fog. Each involves water phase changes: freezing, melting, condensing, evaporating, that store or release energy. Weather patterns are essentially water patterns, moisture moving through the atmosphere, driven by temperature differences, shaped by Earth's rotation and geography. Understanding water is essential to understanding weather. Meteorologists track moisture, where it is, how much, where it's moving. The role of water in weather makes climate change complex. Warming affects evaporation rates, precipitation patterns, storm intensity. Changes in water cycling mean changes in weather, which affect ecosystems, agriculture, and human societies. Water is the medium through which climate expresses itself. The creation of storms and rainfall. Storms form when conditions align. Moisture, instability, lift. Warm, moist air rises, cools, and condenses, forming clouds. If the atmosphere is unstable, cooler air above warm air, rising continues vigorously. Condensation releases latent heat, warming the air further, accelerating the rise. Cumulonimbus clouds tower to the stratosphere. Inside, updrafts and downdrafts create turbulence. Water droplets collide, growing into raindrops. Ice crystals form at high altitudes. When droplets become too heavy, they fall as rain. Intense updrafts create hail, lifting raindrops repeatedly through freezing levels until they grow large. Lightning occurs from charge separation within clouds, discharging between cloud and ground, or within clouds. Thunder is the sound of rapidly expanding air heated by lightning. The creation of storms and rainfall is chaotic, yet follows physical laws. Meteorologists predict storms by modeling atmospheric conditions, tracking moisture and energy. But storms are complex, sensitive to small changes, sometimes defying prediction. Storms and rainfall are essential. They redistribute heat and moisture, water the land, fill rivers and aquifers. Too much causes floods, too little causes drought. The creation of storms and rainfall is nature's way of balancing, moving excess moisture from oceans to land, releasing energy accumulated through evaporation. It's violent sometimes, gentle others, but always necessary, part of the endless circulation that sustains life. The calm after the storm. When storms pass, stillness follows. The air is clear, washed clean of dust and pollen. Colors seem brighter. The light is soft, filtered through departing clouds. Puddles reflect the sky. Leaves drip slowly. There's a freshness, a sense of renewal. The calm after the storm is more than psychological. It's physical. The atmosphere is cleaner. Negative ions are abundant. Temperature has moderated. Plants are refreshed. Dust removed from leaves. Soil moistened. Streams run full. The landscape has been transformed. Sometimes subtly, sometimes dramatically if the storm was severe. The calm, after the storm, offers reflection. Damage may need repair. Flooding may have occurred. But there's also relief that the violence has passed. Gratitude for survival. Appreciation for normalcy. Nature resumes. Birds emerge, sing, search for food. Insects take flight. Life continues. The calm after the storm is temporary. Another storm will come eventually, but in the interim, there's peace. The calm after the storm reminds us that intensity cannot be sustained indefinitely, that rest follows exertion, that turbulence gives way to tranquility. It's part of water's rhythm, gathering, releasing, settling, a cycle of tension and release that shapes both weather and our experience of it. The colors of the sea and sky. Water and sky share colors, each reflecting the other. The ocean appears blue because water absorbs red and yellow wavelengths, scattering blue. Deeper water is darker blue, shallow water lighter, sometimes turquoise where white sand reflects beneath. Near coasts, suspended sediment can make water green, brown, or gray. The sky is blue for similar reasons. Atmospheric gases scatter blue light more than other wavelengths. At sunrise and sunset, light travels through more atmosphere, scattering away blue and leaving reds, oranges, pinks. These colors reflect on water, painting seas and lakes with warm hues. Clouds add complexity. White when reflecting sunlight, gray when thick enough to block it, brilliant colors when backlit by the rising or setting sun. The colors of the sea and sky are physics, light interacting with molecules, scattering, absorbing, reflecting. Yet they're also emotional, influencing mood and culture. Blue is associated with calm tranquility. Storm gray evokes tension. Golden sunsets inspire. The colors of the sea and sky connect the elements, creating visual harmony, reminding us that water and air are partners in shaping our world and our perception of it. The reflection of light on water. Water reflects light beautifully. A calm lake mirrors the sky. Trees, mountains, a perfect inversion. Moving water fragments, reflections into shimmering patterns. Sunlight on waves creates sparkles, countless points of light dancing. This reflection is specular when the surface is smooth, diffuse when it's rough. The angle matters too. At low angles, water reflects more light. Think of sunset glints stretching across the sea. At higher angles, more light penetrates, revealing underwater features. The reflection of light on water has inspired artists for millennia. Water in paintings captures mood. Calm reflections suggest peace. Turbulent surfaces suggest energy. Photographers chase the golden hour when warm light reflects perfectly off still waters. The reflection of light on water is also functional. It helps aquatic predators detect prey breaking the surface. It allows birds to spot fish. It warms water, driving evaporation. The reflection of light on water is simultaneously aesthetic and practical, a phenomenon that beautifies while participating in essential processes. Watching light play on water is meditative, endlessly variable, never quite the same twice, reminding us that water is dynamic, always interacting with its environment, always beautiful. The sound of waves and rainfall. Water makes music. Waves crashing on shores produce rhythmic roars and hisses, a natural percussion that varies with wave size and beach composition. Gentle lapping on lake shores creates soft, repetitive sounds. Brooks babble, streams gurgle, waterfalls roar. Each has its characteristic voice. Rain adds more textures, patter on leaves, drumming on roofs, splashing in puddles. Heavy rain is loud, overwhelming. Light rain is gentle, soothing. The sound of waves and rainfall affects us deeply. Many find these sounds calming, using recordings for sleep or meditation. There's something primal about it, perhaps because water sounds signaled resource availability to our ancestors. The sound of waves and rainfall is also informative. Sailors read the sea by sound. Foresters gauge rainfall intensity by listening. The sounds tell stories: where water is, how much, how fast it's moving. The sound of waves and rainfall is part of nature's soundscape, acoustic ecology shaped by water's movements. Silence where water sounds should be can be eerie: a waterfall gone dry, a stream vanished. The sound of waves and rainfall is reassurance, evidence of water's presence, continuity, the endless cycle that sustains all life. The healing power of water. Water heals. Physically, it cleanses wounds, reduces swelling through cold application, eases muscles through warmth. Hydration is healing. Dehydration impairs recovery from illness and injury. Psychologically, water soothes. Being near water, oceans, lakes, rivers, reduces stress, lowers blood pressure, improves mood. This is sometimes called blue space therapy, analogous to forest bathing. The sound, sight, and even smell of water calm the nervous system. Swimming and hydrotherapy ease joint pain and improve circulation. Thermal springs have been used medicinally for millennia. The healing power of water extends to symbolism. Water represents purification in many cultures. Baptism, ritual washing, cleansing negative energy. Water rituals mark transitions, renewal, fresh starts. Whether the healing is physical, psychological, or spiritual, water plays a role. The healing power of water may be partly evolutionary. We're drawn to water because it's essential for survival, but it's also experiential. Water is gentle, powerful, constant. It moves without force, flows around obstacles, persists. These qualities inspire, comfort, heal. The healing power of water is real, whether measured in stress hormones or felt in the heart. Water heals because it is life itself. The way water soothes the mind. There's something about water that quiets mental chatter. Watching waves, listening to rain, floating in a pool. These activities induce calm. Neuroscience suggests water sounds and sights engage the brain's default mode network, associated with rest and internal reflection. The gentle stimulation is enough to hold attention, without demanding active processing, allowing the mind to wander peacefully. The way water soothes the mind may relate to rhythm. Waves, rain, streams all have repetitive patterns that entrain brain waves towards slower, more relaxed frequencies. It may relate to negative ions generated near moving water, though evidence is mixed. It may simply be that water is inherently pleasant. We're 60% water ourselves, evolved from aquatic ancestors, drawn to it instinctively. The way water soothes the mind makes it therapeutic. Anxiety eases near water. Creativity flows. Problems that seemed insurmountable become manageable. Water provides perspective. It's been here far longer than us, will outlast us, continues regardless of our troubles. The way water soothes the mind is a gift, one we can access by simply spending time near it, listening, watching, allowing it to remind us that flow is natural, change is constant, and calm is always available if we're willing to find it. The symbolism of purity and renewal. Water symbolizes purity across cultures. It washes away dirt, metaphorically cleansing sin, negativity, the past. Baptism represents spiritual rebirth through water. Ritual bathing in the Ganges, the Jordan, or sacred springs purifies body and soul. Water's association with purity makes sense. It dissolves and carries away impurities, leaving things clean. Water also symbolizes renewal. Spring rains end winter dormancy. Rivers renew through flooding, depositing fertile sediment. The cycle itself is renewal. Water evaporates, falls, flows, evaporates again, eternally refreshed. Nothing is wasted, nothing lost, just transformed. The symbolism of purity and renewal gives water spiritual significance. Holy water, blessed springs, ritual immersion. These practices honor water's power to cleanse and restore. Even secular society recognizes this, turning over a new leaf. Wiping the slate clean, water metaphors permeate language. The symbolism of purity and renewal reflects water's actual properties. It does clean, it does renew landscapes and life. The symbolism is grounded in reality, making it powerful and enduring. Water reminds us that renewal is possible, that we can wash away the past, start fresh, flow forward. The symbolism of purity and renewal is hope, expressed in liquid form. The sacred waters of ancient cultures. Ancient cultures revered water. The Nile was life to Egyptians, a god whose flooding meant survival or famine. Mesopotamians honored the Tigris and Euphrates, rivers that birthed civilization. Hindus consider the Ganges sacred, its waters purifying. Celtic cultures worshipped springs and wells, leaving offerings, seeking healing. Native American traditions recognize water as life-giver, to be honored and protected. Pacific Islanders navigated by reading water, living in intimate relationship with the sea. The sacred waters of ancient cultures reflect water's centrality to existence. Without it, there is no life. Cultures arose along rivers, lakes, coastlines. Water determined settlement patterns, trade routes, prosperity. Honoring water wasn't just spiritual. It was practical acknowledgement of dependence. The sacred waters of ancient cultures often had guardians, priests, shamans, community leaders who regulated use, maintained purity. Water was shared resource, requiring stewardship. Modern society often treats water as commodity rather than sacred trust. Perhaps we've lost something. The sacred waters of ancient cultures remind us that water deserves reverence, care, gratitude. It sustains us still, as it sustained our ancestors. Treating it as sacred might ensure it remains abundant for future generations. The importance of rivers in civilization. Rivers made civilization possible. The first cities arose along rivers: Nile, Tigris, Euphrates, Indus, Yellow River. Rivers provided water for drinking and irrigation. They transported goods and people. They deposited fertile sediment during floods, enriching soil. Civilizations rose and fell with river health. Mesopotamia collapsed, partly due to soil salinization from irrigation. The Indus Valley civilization may have declined as rivers shifted course. The importance of rivers in civilization continues. Cities still cluster along rivers. Commerce follows water routes. Hydroelectric dams generate power. Rivers remain central to human geography. They're also sources of conflict. Water rights, dam construction, pollution. These create tensions between regions and nations. Shared rivers require cooperation and diplomacy. The importance of rivers in civilization extends beyond utility. Rivers feature in art, literature, music. They're cultural touchstones, identity markers. Old Man River, the Seine, the Thames. Rivers have personalities, histories, significance beyond their physical presence. The importance of rivers in civilization is both practical and symbolic. Their infrastructure and inspiration, resources, and retreats. Protecting rivers protects our past, present, and future. They connect us to ancestors who settled their banks and to descendants who will depend on them still. The bridges between land and sea. Estuaries are where rivers meet the sea, mixing fresh water with salt water, creating unique ecosystems. These transitional zones are incredibly productive, supporting fish, birds, invertebrates, and plants. Adapted to fluctuating salinity, estuaries serve as nurseries for many marine species. Fish and crustaceans spawn in protected waters before juveniles venture to the open ocean. Mangroves and salt marshes and estuaries stabilize shorelines, filter pollutants, sequester carbon. The bridges between land and sea are also corridors for migratory species, salmon swimming upstream to spawn, eels traveling from rivers to the Sargasso Sea. Estuaries accumulate nutrients washed from land, supporting rich food webs. They're vulnerable, however, to pollution, development, and sea level rise. Many estuaries worldwide are degraded, their productivity diminished. The bridges between land and sea connect terrestrial and marine realms, freshwater and saltwater systems. They're meeting places, interfaces, where different environments blend. Protecting estuaries means protecting coastal fisheries, storm buffers, and biodiversity hotspots. The bridges between land and sea remind us that boundaries aren't absolute. Water flows from mountains to oceans, connecting all points between. Estuaries are emblematic of this connectivity, reminding us that protecting one ecosystem requires protecting all connected to it. The hidden water in the air. Air contains water you can't see. Vapor, molecules dispersed among nitrogen and oxygen. Humidity measures this invisible water. Warm air holds more vapor than cold. That's why tropical air feels heavy, desert air light. The hidden water in the air is essential for weather. Without it, no clouds, no rain, no storms. It also affects comfort. High humidity makes heat feel hotter because sweat doesn't evaporate efficiently. Low humidity dries skin and respiratory passages. The hidden water in the air becomes visible when it condenses dew on grass, fog blanketing valleys, your breath on cold mornings. These are water vapor returning to liquid form, made visible by temperature changes. The hidden water in the air is part of the hydrological cycle's atmospheric phase. It rises from evaporation, drifts with winds, redistributes moisture across continents. Atmospheric rivers, narrow bands of concentrated water vapor, transport vast quantities, releasing them as rain or snow when they encounter mountains or cold air. The hidden water in the air is substantial. If all atmospheric water vapor condensed simultaneously, it would cover Earth's surface about 1 inch deep. The hidden water in the air is invisible, but omnipresent, connecting surface water to sky, participating constantly in the cycle that sustains all life. The humidity that shapes our climate. Humidity isn't just comfort or discomfort, it shapes climate. Water vapor is a greenhouse gas, trapping heat and warming the atmosphere. It's responsible for more than half of the greenhouse effect, though its role is complex, because it responds to temperature rather than directly driving it. Warmer air holds more moisture, which traps more heat. creating feedback loops. Humidity also affects precipitation patterns. Moist air produces rain and snow. Dry air doesn't. Deserts exist partly due to descending dry air in atmospheric circulation cells. Rainforests exist where humid air rises and cools, releasing moisture. The humidity that shapes our climate varies globally. Equatorial regions are humid, polar regions dry. Monsoons are seasonal shifts in humidity and precipitation, driven by temperature differences between land and sea. The humidity that shapes our climate is changing. As Earth warms, evaporation increases, raising atmospheric moisture. This intensifies the water cycle. Heavier rains, worse droughts, stronger storms. Understanding humidity's role in climate is crucial for predicting future conditions. The humidity that shapes our climate is invisible yet powerful, influencing temperature, precipitation, and weather patterns worldwide. It's another reminder that water, even as vapor, profoundly affects the planet. The scarcity of fresh water on Earth. Earth has abundant water, but most is salty. Oceans hold 97% of the remaining 3% fresh water. About 70% is frozen in ice caps and glaciers. Inaccessible, much of the rest is underground. Not all easily reachable. Rivers and lakes, the fresh water we see, contain less than 1% of Earth's water. The scarcity of fresh water on Earth means accessible supplies are limited. Billions of people lack reliable access to clean water. Agriculture consumes 70% of freshwater withdrawals. Industry and households use the rest. Competition for water intensifies as populations grow and climates change. Some regions are water-rich, others water-scarce. This inequality creates conflict and migration. The scarcity of fresh water on Earth is worsening. Climate change alters precipitation patterns. Some areas get wetter, others drier. Glaciers shrinking means losing stored fresh water. Pollution renders available water unusable. The scarcity of fresh water on Earth demands conservation, better management and technology, desalination, recycling, efficiency improvements. It also demands equity, ensuring everyone has access to this essential resource. Water scarcity isn't inevitable. Earth has enough water if managed wisely. The scarcity of fresh water on Earth is a distribution and management challenge, as much as a physical one. The global flow of oceans and rivers. Water flows globally, connecting all points. Rivers carry water from mountains to seas. Ocean currents circulate water between hemispheres and depths. Atmospheric moisture moves over continents, falls as precipitation, rejoins rivers. This global flow is the hydrological cycle at its largest scale. It distributes heat, nutrients, and life. The thermohaline circulation, sometimes called the ocean's conveyor belt, moves water around the globe over centuries. Warm surface water flows from the tropics toward poles, cools, sinks, and returns along the bottom. This circulation influences climate worldwide. Disrupting it could cause dramatic climate shifts. The global flow of oceans and rivers means that what happens in one place affects others. Pollution in a river reaches the sea. Deforestation in one region reduces rainfall in another. Melting glaciers raise sea levels globally. The global flow of oceans and rivers is planetary connectivity made liquid. It reminds us that Earth is a closed system. Water cycles but doesn't leave. Everything is connected through water's movement. The global flow of oceans and rivers is beautiful in concept and essential in function. Understanding it is understanding how Earth works, how systems interconnect, how actions have distant consequences. The cycle of life and water together. Life and water are inseparable. Life began in water and remains dependent on it. The water cycle and life cycles intertwine. Plants transpire, contributing moisture to the atmosphere. Animals drink, metabolize, excrete, returning water to the environment. Decomposers break down organic matter, releasing water. Ecosystems are water systems. Food webs follow water and nutrients. Remove water, and life collapses. The cycle of life and water together is reciprocal. Life affects water's movement and quality. Water affects life's distribution and abundance. Wetlands filter water while providing habitat. Forests generate rainfall while stabilizing watersheds. The cycle of life and water together is resilience. One supports the other. Protecting water means protecting life. Protecting life means protecting water. They're not separate concerns. The cycle of life and water together has operated for billions of years, evolving, adapting, continuing despite challenges. Climate change, pollution, overuse, these threaten both life and water, but understanding their interconnection offers hope. Solutions that benefit water benefit life, and vice versa. The cycle of life and water together is the story of Earth, a partnership that has shaped the planet and made it uniquely alive, a blue jewel in the cosmic darkness. The future of Earth's water. What does water's future hold? It depends on us. Climate change is altering the water cycle. More intense storms, longer droughts, melting ice, rising seas. These changes threaten water security, ecosystems, and human societies. But the future isn't fixed. Choices matter. Reducing emissions slows warming, moderating changes, protecting watersheds, maintains water quality and supply. Efficient use stretches limited resources. Technology offers solutions. Desalination, wastewater recycling, smart irrigation, nature-based solutions work too. Wetland restoration, reforestation, sustainable agriculture. The future of Earth's water can be hopeful if we act wisely. Water will continue cycling regardless. It's resilient, ancient, patient, but its distribution, quality, and accessibility for humans and ecosystems depend on decisions made now. The future of Earth's water is also opportunity. Water connects issues: climate, food, energy, health. Solving water challenges addresses multiple problems. The future of Earth's water is uncertain, but not predetermined. It's being written now through policies, practices, and priorities. What kind of water future do we want? One where everyone has clean water, where ecosystems thrive, where rivers run clear and oceans are healthy. That future is possible, but it requires care, foresight, and respect for the substance that makes life possible. The need to protect what sustains us. Water sustains us, yet we often take it for granted. Turn a tap, and water flows. But behind that convenience lies infrastructure, watersheds, ecosystems working together. The need to protect what sustains us is urgent. Pollution degrades water quality. Overuse depletes aquifers and rivers. Climate change disrupts patterns. These threats are self-inflicted, but they're also solvable. Protecting water means protecting sources, keeping forests intact, preventing pollution, managing land sustainably. It means using water wisely, fixing leaks, improving efficiency, recycling where possible. It means recognizing water's value beyond economics, cultural, spiritual, ecological value that can't be quantified but is immeasurable nonetheless. The need to protect what sustains us is both practical and ethical. Practically, we depend on water for survival, food, energy, industry. Damaging water systems damages our future. Ethically, water is life. Polluting it harms not just humans, but countless species. The need to protect what sustains us is a call to stewardship, to caring for the resource that cares for us. Water has sustained life for billions of years. Will we sustain it for billions more? The answer depends on whether we recognize water not as commodity, but as sacred trust, deserving protection, respect, and gratitude. The endless motion of the seas. Oceans never rest. Currents flow ceaselessly, driven by wind, temperature, and Earth's rotation. Tides rise and fall with lunar rhythm. Waves roll across surfaces, transferring energy from storms thousands of kilometers away. The endless motion of the seas is planetary circulation, heat distribution, climate regulation. It's also beautiful. Watching the sea, you see constant change, patterns emerging and dissolving, light playing on moving water. The endless motion of the seas is life-giving. Currents carry nutrients, supporting marine ecosystems. Mixing brings deep, cold, nutrient-rich water to the surface, where phytoplankton bloom. Wave action oxygenates water. The motion prevents stagnation, keeps the ocean alive. The endless motion of the seas is also power. Wave and tidal energy can generate electricity. Ocean currents have been highways for exploration and commerce throughout human history. The endless motion of the seas reminds us of time's passage. Waves keep coming, one after another, endlessly. The sea was here before us, will remain after. Its motion is continuity, persistence, the heartbeat of a living planet. The endless motion of the seas is soothing in its constancy. Whatever happens on land, the sea keeps moving, keeps flowing, keeps being itself, vast, powerful, eternal. The eternal journey of a single drop. And so we return to where we began. A single drop of water. It might be in a cloud right now, or falling as rain, or flowing in a river toward the sea. It might be in the ocean, or frozen in a glacier, or underground in an aquifer. It might be in a tree's leaf, or in your body, or in a puddle, evaporating in the sun. That drop has no beginning and no end, just transformation. It's been everywhere, part of everything, cycling endlessly through states and places. The eternal journey of a single drop is the story of all water, ancient yet ever-present, simple yet essential. That drop connects past and future, sky and earth, life and landscape. It's the same drop that filled ancient seas, fell on dinosaurs, sustained early humans. It's the drop that will fall as rain tomorrow, fill rivers next year, be drunk by your descendants centuries hence. The eternal journey of a single drop is immortality, not of form, but of substance. Water persisting, transforming, continuing forever. As you drift to sleep tonight, think of that drop, its journey through time and space, how it's touched everything, connected everything, made everything possible. You're part of that journey, carrying water within you, participating in the cycle. Rest well, knowing that water's story is your story, that you're held in the same flow that has sustained life since the beginning, that will continue flowing long after the last word is spoken. Good night.